Okay, welcome everyone to how to review session presented by me, Cody fan, your biggest fan, HKN's internal VP. Yeah, I hope you like the WikiHow meme of how to stop a robbery. Okay. So Nico, you wanna tell
Yeah,
them about
sure.
good content?
Yeah, so we'll go ahead and get started with what exactly it means to host a review session. So first of all, I forgot to introduce myself. My name is Nico. I'm the current president of HKN here, and I've been hosting review sessions since I was an officer. And I gotta say, it's one of my favorite parts of HKN. So the way to host a review session is you first want to, assemble all your content, and you want to figure out what exactly you're hosting a review session about. Usually that will involve looking at the syllabus. Cody, if you can,
Oh yeah.
yeah, looking at the syllabus. Contacting the professor, asking them, hey, what are you going to be covering by the time of the midterm? After that, it'll cover Cody. You want to look at previous exams in the textbook, right? You want to be sort of figuring out what sort of questions the professor asks, and you want to just generally review the material for yourself, get your understanding back where it was when you were taking the class. And then the last thing would be you want to figure out what sort of tricks you used to have for solving the problems that either the professor that you knew had, or just general tricks for solving the problems that you found most difficult in the class. So if you've ever had a class with Professor Robert Candler, you will probably have seen this graph before. This is a graph of how students' attention spans work over time. So generally the idea is that if you give a student a test after their the class that you're with all the material you're teaching them, their performance is sort of follows this very strange parabola that decreases with time, um, and will often decrease more and more as the lecture goes on. So the way to combat that is that you give rest periods, and then you also give activity breaks where that actually engages the student's mind. Professor Candler does this by asking questions and throwing candy at students, which is a little bit difficult in Zoom times. So instead, oftentimes the best thing to do is to, ask the most engaging questions you can, maybe break people out into breakout rooms and have them solve a problem together. And generally that's a good way to go about doing review sessions. So after this, there's a couple of general methods that you want to implement while you're assembling the material and sort of as you're planning out how your review session is going to go. So, Cody, first thing is going to be your means of communication, right? How are you going to communicate the general ideas and remind students of the concepts? Um, in general, the best way to do that is with visuals. If you can get sort of a visual idea, or if you get an idea in a visual setting, it's a lot easier to remember than it is, in some sort of written out sense. Oftentimes, that's why mathematical equations are useful, because it sort of explains a concept in a couple of smaller symbols, or more narrowed down symbols. But generally, slideshows and having an iPad and writing on it are two great ways to communicate these things. And then after this, how you instruct them in sort of and break out your actual review session in terms of time. So not just the actual content, but more or less what you're doing step by step. So this includes practice problems and examples that maybe your instructor did. And again, like I said, breakout room problems. Um, or you have sort of you just go straight with the theory, right? You just sort of have a direct explanation of it, and then maybe you break students out into different rooms and let them sort of explain to each other these concepts on their own. um, Again, you always want to be making sure the students are engaged, and you want to make sure that these students sort of have a bit of room to breathe on their own, and sort of work their own mind. Now, when it comes down to it, there's only so much you can do, right? If students don't want to be engaged, then you can't really do anything about that. And if they're like actively trying to not be engaged, it's a bit difficult, but oftentimes, you know, as Dr. Candler will say, throwing candy at them, at anyone will get them involved. So that's generally the way that you want to think about structuring your review. And from there, I'll leave it to Cody to give a couple more tips and tricks.
Yeah. So sometimes you get distracted. Like, hey, look, a squirrel. So to avoid this, you might want to try putting students in the breakout rooms every so often. And like, it's a good idea to just let the students get to know each other and like be social. So maybe the first one is just like introduce each other. And then the ones after that can just be like answering a question that you might have prepared, like a practice question. And yeah, like as mentioned before, if you ever had Rob Candler, he's a good professor, just do what he does. And memes are pretty cool. If you ever had AJ, is a really good TA in like 113. Yeah, he has like memes on his slides, and he's pretty informal when he explains stuff. So, you know, you could put like, if you're doing an EE2 review session, you could put like, you know, P-type semiconductor exists, you know, these types of memes. Or you could put like this type of meme if you're doing like circuits, right? Listening to AC/DC and you're listening to the signal coming out of the socket. Also, it's okay to like mess things up. You know, because like at the end of the day, it's like you doing and showing up and helping them prepare for the exam is better than you not being there to help them prepare for the exam. So if only like 2 people shows up, it doesn't mean that you're unpopular. It just means that you can give them more personalized help. If if you said that 1 + 1 = 3, well, I mean, you can just go back and correct yourself, or if you, yeah, and maybe someone will catch it and they'll be like, wait, that's not right. And it's good to admit your mistakes. And if people like they just don't want to participate, then I mean it's their problem, because I mean it's their class and it's their exam. So yeah. And if you can't cover the entire syllabus, I mean that's fine. Just cover a good chunk of it. Yeah.
So with that, just before, what we're going to do is we're going to go into breakout rooms and let you guys sort of pick a topic on your own, any topic you want, and try to explain it, sort of format something, take 5 minutes to try to figure out if you can, format an idea that you're going to try to explain to your colleague, and then you're going to explain to your colleague. But before that, I'll give a quick explanation of Fourier transforms. So the idea behind Fourier transforms is that these sinusoids that we see everywhere, that you've seen since trigonometry, sort of act like vectors, and that when you're trying to make a function, right, or when you have a function, you can actually describe it as if it's just a sum of different vectors. Next slide, Cody. So this sort of starts with the idea, again, that every exponential is itself just a vector, right? And that, more importantly, that there is a sort of dot product operation. If you remember linear algebra, a inner product will sort of take the projection of a vector, of one vector onto another, right? And that operation is shown here in that when two frequencies are the same, that's the same as them being one over, or being a delta function over an integral from -infinity to +infinity. That is, that when they're the same, the answer is 1, right? So you sort of get an exact projection of one frequency onto another. But when they are not the same, then you will get 0. So that's the idea there. Next slide. So then if you have a function that you can, and so then you can assume that a function can be described as a sum of these exponentials, and more importantly, as a sum of these sinusoids. And you can put them together to build up your function in the same way that you would put a set of vectors together to build up, another vector in, for example, a 2D plane. Next slide. And then the transform is telling us sort of, how much weight is on each vector. So if you were to, look at, if you were to actually do this transform, right, this function f, capital F of omega prime would tell you, how much of each sinusoid of frequency omega prime is inside my function little f of x. And that's sort of the idea there. And once we have all those, we can sum, once we have all of these weights, we can sum every single sinusoid of each frequency together and eventually start forming something that looks like a square wave. So with that, let's go ahead and practice. So we'll split you guys up into breakout rooms, and you guys can choose a random topic, whatever you want, and you can sort of explain to each other. Or we just do it here. I don't know, there's only 4 of you, really, 3 of you, actually. And then I think Selene just said that she has to go to a meeting. So it's really only you, Vaibhav, and Linfeng. So if you guys want, you can just choose a random topic. We'll give you guys 5 minutes. And it doesn't, don't feel like you want it to be restricted to anything in particular. If you don't want it to be, studious or school related, that's perfectly fine. If you have something else that's interesting to you, I debated doing surfing. I surf a lot, and I sort of would have been interested in explaining, maybe the breaking down how surfing works. Either way, we'll go ahead and give you guys 5 minutes, and you can get started on that. I'll set a timer right now. Since it's 5 minutes, we're not expecting anything. We just want you to, get the brain going. Sorry, Selene. I should have done surfing. Maybe I'll think about that while you guys are thinking about this, and we can come back together and we can sort of, pass the baton a little bit.
Sorry, I actually have to hop out because I have a meeting, but thank you so much.
Yeah, no worries.
No worries.
All right, bye guys.
Um, I mean, I can do circuits, I suppose. I
Sure.
don't know, like that's kind of what I've always enjoyed the most. I think I don't know if this is like something all professors do, but Abidi had a really cool way of explaining capacitors and inductors, which I think makes it a fair bit more intuitive than having to memorize that capacitors don't like sudden changes in voltage and inductors don't like sudden changes in current. I see Cody smiling. I think he remembers this. Um, well,
All right. Looks like you're gonna be the only one who gets credit for this vibe off because.
all right. Let's give this a spin then. Oh yeah, introduce myself first, right? I'm Vaibhav. I'm a junior. The favorite class I've taken, probably EE10, either EE10 or EE115A. Even then, probably EE10. I really enjoy that course. Kind of set the foundation for where I'm taking my degree, so I enjoyed it a fair bit. So random topic, setting initial conditions when you're solving a circuit problem, because that's really important, especially in EE10, because before you get into the differential equations are a whole bunch of math. You either do it right or you don't, honestly. You kind of just have to go through it. But where it's more intuition based and more knowledge based is setting the initial conditions for a problem and making sure that when the switches in the system kind of go on and off, which is how a lot of those problems are built, you know what starts happening and what doesn't happen. And so a good way to think about it for capacitors and inductors is to look at their characteristic equations, where we say for a capacitor, what was it? Q is equal to CV, so I is equal to C dV dt. And so a good way to think about why a capacitor. Wait, hang on a second. Right. Sorry. Yeah. So a good way to think about why a capacitor doesn't let the voltage across it change is because change in instantaneously, and why when a switch turns on or off, the voltage across a capacitor will generally on the either side of that instant stay the same, is because for the voltage to change, you would need an infinite current, and no supply can provide said infinite current. And so you can use that characteristic equation to reason your way into proving to yourself that the voltage across a capacitor can't change instantaneously. And you can do the same thing for an inductor, where you can say that for the current through this inductor to change instantaneously, I would need an infinite voltage. And I know that any source can't provide an infinite voltage. And so I can reason to myself quite intuitively from just that characteristic equation that the current through this can't change infinitely. And I found that really helpful because it meant that I didn't have to memorize these conditions that, like I already showed in these 2 minutes, I used to keep getting confused and muddled up. And so it makes it much easier to just keep track of a few very simple equations and then just think your way through those. And this is it's a really cool trick that I think helped me make sure I got my initial conditions right in E10 and 110.
Cool. That's great. Yeah. I think I learned something very similar in E10, and definitely that's a good line of reasoning for that. So yeah, that works really well. What sort of I know obviously you can't like just call it visuals from, or like make visuals right now, but what sort of visuals do you think you'd use for explaining that, other than just that's a harder one. So
Yeah.
don't worry too much about that. Sometimes you just have to use the math.
Yeah, I don't know.
That's
I'd
sometimes what I
probably
do.
have a picture of the, C equals what is it, I equals to C dv dt, and then the um, V is equal to L di dt, just equations up there. Another thing that is important to keep track of with those equations is convention about current flowing into the positive end. I know that that's how I lost a fair bit of points on my E10 midterm, because he had current flowing into the negative end of one of the capacitors on this one circuit, and I just didn't catch that.
Yeah, that sounds that's pretty important. Also becomes important. Have you taken analog circuits yet?
I took 115A.
Yeah, okay.
Yeah.
I found that was super important there. Like all the time I was like, oh, I got to make sure that I'm not messing up any signs here. Otherwise I'm going to put a negative sign somewhere, add some currents wrong, and I'm just going to get everything wrong. So yeah, that's good. That's good. Cool. I think, I mean, I hope that you took something from this workshop. Are you interested in helping out with any of the review sessions?
Yeah, I mean, on the form